This is my presentation of the convex hull algorithm known as GramScan or Grams scan. Not really sure. I think it was invented by a dude named Graham. So, first off, purpose of this algorithm. If you look right here, I know it's kind of hard to see, but suppose that you have a collection of points, right? This can just be like a list or an array or whatever of like XY coordinate pairs or I don't know, what have you, like points or whatever. Suppose that you want to find the list of points that can, when connected, encircle all points in the thing while forming a convex shape. And well, the reason you wanted a convex shape is to minimize the perimeter, right? So it's pretty easy to do intuitively as like, oh wait, that's a mistake. Those two guys are coterminal. So there we go. It's pretty intuitive as a human being to do this. It's basically just connect the dots, right? Um, and then here you can see I've encircled every single point. That right there, it's like just because I don't want these markers to bleed into each other. Um, but yeah, this outline I've drawn encircles all points on the inside of the thing, right? So, question is, how do we do this algorithmically? So, um, the way that it works is we start, this right here is our list of points, right? We start by finding what I'm going to call the minimum or like focal point. This is where we're going to be doing the scanning from. So from what I understand, traditionally this is done by finding the point with the lowest y value, right? Right here. And then if there's multiple points that have the same y value, which is pretty common, especially if you're doing a convex hull algorithm with an image or something, then you just take the one with the least x value. So lowest, leftmost, right? So this guy right here, this guy right here is our minimum. All right, so then what we do is we're going to sort our remaining points by their angle from the midpoint. And we can do this pretty easily using a trigonometric function that's available on pretty much every computer system. Uh, arctangent 2, right? So arctangent 2 takes a y and then an x. And the way that this works is if you have a unit circle like this, basically you give it like, I don't know, you give it some point on the circle. I'll draw that a little bigger so that you can see. Yeah, there you go. You give it some point on the circle, right? And really this point is just like this is the y, this is the x, and then this angle right here is our theta. So tangent would give you like sine of theta over cosine of theta. Arctangent does the reverse of that. So you give it like y over x, and it'll give you theta. So here, the cool thing about arctangent is by default it does it from like 0, 0 to like whatever that point is that you give it. But what we do here is let's see, what we do here is we have like 2 points. So this is like point 1, this point, or this point 0, this is point 1. So we do like x1, or wait, yeah, x2 minus x1 as the denominator, and then we do y2 minus y1 as the numerator, right? And then mathematically, if we do arctangent on this, it'll give us our angle that we want to sort by, right? Arctangent 2 just means arctangent with two arguments. So instead of having like numerator, denominator, you just have the y and the x. So this will just be y2 minus y1, and the second argument is x2 minus x1, right? So that's pretty straightforward. And the way I like to think about this is we kind of draw a line in our heads between each of these points. And as you can see, they kind of like, it's like a fan, you know? And the way that like the way that radian angle measures work because of the unit circle. Oh my gosh, I'm drawing another unit circle. Here we go. This right here is 0 or 2 pi. This over here is pi, right? So the least angle is like this, right? So angles that are closer to this, like this one right here, are going to be lower. So the ordering of this is going to get sorted as like 1, 2, 3, 4, 5, 6, 7, 8, right? So that's pretty straightforward. And because this sorting step is usually going to be log of n, it'll be like, or n log n? Log n log n, doesn't really matter. That's just going to add that to the complexity of this whole thing. So we have our sorted array of points. And now what we can do is we can iterate through them and add them to our whole list. So over here, I'm gonna like, I don't know, make like a list right here that's gonna hold our points, you know? So the first thing in the whole is gonna be min, right? Because this is gonna be the start and the end of our convex hull. That's one important thing. Oh shoot, drop that. That's one important thing to remember about convex hull because it is like a path. Traditionally, we will have the starting point, not a path. We'll have the starting point and the ending point be the same. So we'll add min again to it at the end. So we start here, and then we'll just automatically add 1. We'll add 0.1. Maybe I should write like p1, so it's not. We know that it's not like just a number. So we add p1, and then we add p2. The reason for this is because 0.1 and 0.2 are, no matter what, going to be the first 2 points in our convex hull, right? It makes sense if you think about it, because if either of them were lower, then they would be the minimum instead. And yeah, yeah, it's whatever. It just works, trust me. So we do this. So minimum 0.1, 0.2. And I like to think of this as like we are now drawing our hull, you know? So minimum goes to 0.1, 0.1 goes to 0.2. I know that looks like a straight line. There's a slight angle, trust me. So then from here, for each item in the rest of our like unevaluated points, we're going to perform this procedure. We take, let's see. Oh, that's what I'm forgetting. We need an orientation procedure, right? So orientation. Orientation. So we need some way to figure out with like point A, point B, and point C, we need to figure out if this angle right here, theta, is going to be like, it's not so much about the angle. It's like, is this making it convex or concave? So concave angles, or wait, convex angles would be like the points are like in here, you know, it's like hugging them. Concave would be like it's concave would be like the points are right here, you know, and it kind of like dips towards them. That increases the overall perimeter. So that's bad because it's inefficient. And that's not what this algorithm is for. It's convex hull. There is no concavity allowed here, right? So I don't fully understand the way that this works because I don't know a lot about vector math, but I know that if you take the vector cross product of A to B and B to C, it will give you a number that's either positive, negative, or zero. And that tells you kind of like the orientation of this, right? So the idea is that when you do the cross product of vectors, it gives you a third vector that's like, I don't remember the thing for like the magnitude of the vector, but it gives you a third vector which is perpendicular to both vectors, right? So like the way to remember it that I've seen is like if you look at this, it's like this is like my thumb's like the y-axis, this is like the x-axis, and then my middle finger is like the z-axis, right? So it's like if you if this one is like this and they're like this and it's pointing this way, that means that like the cross product will be like coming out towards the viewer. But if it's the other way where it's like this, then it'll be going into the board, and that's how we know that it's like convex or concave. Don't worry about it too much. You can just look it up. It's a pretty simple implementation, and I'll show you in a minute how I actually coded that. So now that we know how to determine whether a connection between points will make it convex or concave, we can just start adding and evaluating points, right? So we're going to skip 1 and 2, and we're going to go straight to 3. Now, before we actually add 3 to our whole, we're going to evaluate, like, assuming that 3 is part of our whole, does the line between, like, 1 to 2 and 2 to 3 make it concave or convex, right? So it's like, we see this, we can tell this belongs here, right? Makes it concave. So we're just going to do nothing and add 0.3 to our whole, right? So that's good. And now we come to 0.4, right? Now, oh yeah, orientation, you can think of it as clockwise or counterclockwise, or coterminal, which is where they're just like straight, you know? So we're gonna look at this. We're gonna be like, okay, it's 0.4. This thing right here, is this is a counterclockwise turn, right? Goes like, so perfectly fine. We are all good. So we're gonna go ahead and add 0.4 to our whole. Now, this is where things, oh wait. Oh no, never mind. This isn't where things get interesting yet. We evaluate 0.5, we see it's like, you know what? Yeah, these are coterminal. So we see that this is just like a straight line, right? Like doo, doo, doo. So what we're gonna do is we're gonna remove 0.4 from our list, and we're gonna add 0.5. So right here, we're just gonna, there we go. And then here we have 0.5, right? Now this is where it gets interesting, because 0.6, we evaluate 0.6, and we see 0.6, it's not a clockwise turn, right? Or it's not a counterclockwise turn. Yeah, it's a clockwise turn, because it's like, so 0.6, because point, 0.3 to 0.5, 0.5 to 0.6 makes a clockwise turn, we know that 0.5 does not belong in our whole. So we will remove him. I'm sorry, 5, you've been voted off the whole island. And we are just going to add 6 to our whole, right? So 0.6. Yep. And now, as you can see, this is correct, right? Now, 6 to 7 and 7 to 8 Actually, wait, I guess 3 to 6 and 6 to 7, that's clockwise turns, so I'll just say that we add 0.7. But then 6 to 7 to 8, that's coterminal. So we'll remove 7 and add 8. Didn't bother drawing it because I don't want to take too long. So P8, right? Now P8, we've actually reached the end of our points. So that means that we can now add min to the end of our list, and it's done. Ta-da! We now have this list of things that goes through and encapsulates all of our points, right? Now, some stuff to consider, just the performance-wise. There are a couple of convex hull algorithms. GramScan is like pretty efficient, right? Because GramScan, let's see. Our first step is an O of n thing, right? Finding the minimum in a list, right? Like we find the lowest y, then the lowest x. So that's O of n, right? So then we sort them by their angle, right? Which, because that's a sort, that's O, wait, that's O n log n. That's O n log n plus, then we go through all of our points, which is O of n again, and then we're done. So really, if you do an O of n operation, an n log n operation, and then an n operation, you can kind of simplify that down to just O n log n, right? Because really, like, these two things, there's not really any like looping within looping that happens. So it's just like O n log n, right? Pretty good. Not bad for a convex hull algorithm. This is especially good when you think about using this on something like an image where you just have a huge grid of pixels. Like everything has a neighbor and like a super huge number of your things are all going to be coterminal because it's all in rows and columns and stuff. But yeah, so yeah, that's how it works. Now I'm going to show you how it actually is implemented. Up here you can see I have the vector cross product black magic that makes it all work. Returns -1 clockwise, 1 counterclockwise. That's the happy thing we want to happen. And then coterminal. So then generate hull, we take in a list of points. And first we find the first item of the list once we've ordered it first by the y coordinates and then by the x coordinates. That'll give us the min point. Then we remove min point from that thing because calling atan2 to find the angle between a point and itself is not a good idea. That's how you get divide by 0 errors or whatever, you know. So then here we sort the points by their angle to min point, and I'll show you get angle right here. Get angle, it's literally just point A, point B, math arctangent to b dot y minus a dot y, bx minus ax, right? So we have gotten our min point, we've sorted it, then down here we make our hull list. We add the min point, add the first point, add the second point, because they will always be in the hull guaranteed. Then for each point after that in our points, so this is what makes it like O of n. We get our new point that we're looking at. Then we check the orientation. I didn't actually demonstrate this on the board, but you're actually supposed to not recursively, but like you're supposed to keep doing that step to like eliminate points that cause it to be a clockwise turn until it's all happy. So while the orientation between the second to last item in the hull and the last item in the hull and the new point is not equal to 1, meaning that it is clockwise, we remove the last item from the hull, right? So once that's all squared away, then we just add the new point to the hole. And we do this for each point. And yeah, then, this is important. Just because of the way I implemented it, you actually have to do it one more time because you need to add the minimum point again to the end, right? So second to last item, and the min point, and then we smooth it out from there, right? We add the min point and we return the hole. So let's look at our test. Our test right here. We have our points in our list. These are the points that'll go into the convex hull algorithm. And here we call it. And then this is what it should give out, right? As you can see, beginning and the end are the same point. And so I did that last step. And then here it just asserts. So, actually wait. Yeah, run all. And this should work. If it doesn't, I might cry. Yes, perfect. Yep, 114 milliseconds. Not bad. Test 1, success. So, yeah, that's the algorithm.